All right, let's get started. In this lab session, we're actually going to see how we will be able to implement our K-nearest neighbors, right? It's just like we just had an intuition about what the K-nearest neighbors is all about in the previous video. So in this particular video, we're going to actually have a hands-on and then see how we are going to be implementing this K-nearest neighbor, okay? So we're going to use this data set, which is available at the UCI machine learning repository. Okay, so if you go there, right, I've given you a link here, right? So I'll upload this notebook on the platform so that you get access to it. All right. So if you go to the UCI machine learning repository, right, at this link that I've given you, you'll be able to download the data set that we're going to use over here. And I'll also load, the data set over there in on the platform for you so that you can easily have access to it instead of maybe you go in there into the UCI machine learning repository to download. All right, so this data set contains it contains several columns, or several records, right? Which about a cell, right? Whether a cell is is cancerous or not cancerous, right? So in this case, we have what is called the benign and then the malignant. Okay, so we have what is called the benign and then the malignant. So if we see, if we go into our data set, we're actually going to see what this means, right? The benign, right? And then the malignant, okay? So that's what we are going to actually consider. That's what we're going to do with, right? That's our data set. So let me just, proceed so that when we see the data set itself, we will come back and then talk about what this benign and the malignant means, okay? So let's just move one more step and then see what we are going to do over here. Now, as we did in the previous videos, the first thing you need to do is to load the particular libraries that you're going to need, okay? So in this case, we are just loading the familiar ones that we've been dealing with so far, right? In the likes of NumPy, Pandas, Seaborn, okay? And then the Matplotlib, okay? So all these are libraries that we've been dealing with right from the first tutorial, right from the linear regression class. We've been dealing with this. So I'm sure you are aware of all these libraries, okay? So now, moving on, the next thing that we need to do, this one is just an alternative to, to load these libraries using the PyForest, and I'm sure you've been able to use it, with respect to the various courses that we've had. In the likes of the linear regression, logistic regression, we're using this PyForest, so I'm sure you are able to use this so far, okay? So instead of importing them one by one, you can just use the PyForest to do that. All right, so let's progress and then load our data set over here, okay? Now our data set is actually stored in a file, a CSV file, right? So I'm going to use the read_CSV to read that, okay, which is present in pandas, and then I'll store everything in a variable called df, okay? That's what I'm going to do over here. So if I load that and I see the first 5 rows, all right, so this is what I have in my data set, right? This is what I have. I have several features in here. All right, I have several features in here, as you can see over here. All right, I have several of them. Now, with all these features, right, I have the ID, I have the diagnosis, I have radius mean, texture mean, perimeter mean, area mean, smoothness mean. So most of them, some mean of some features, right? Some texture worst, perimeter worst, right? Area worst, a lot of features that I have over here, right? So all these features are what we are going to use to help us make some predictions whether a cell is going to be benign or malignant. All right, so our target here is this column, right, which is diagnosis, right? That's our target, right? So that's what we actually need to predict. That's going to be our y, and the rest of this all the way to the last part is going to be our x over here. Okay, so this is our target, and that's what we need to predict. So this contains only b, right? B for benign, right? B for benign. Right, and then M, right? It contains B and M, right? Where M is for malignant, right? For malignant. All right, so when we talk about the benign cells, right? When we talk about the benign cells. Benign cells are cells, right? They are cells that are not cancerous, right? They are not cancerous, right? And then the malignant cells are cells that are cancerous. Right, so we want to predict whether a cell is cancerous or not, right? Whether a cell is cancerous or not cancerous, right? So whether a cell is malignant or benign, okay? So we want to predict either M or B, That's what finally we want to do, right? That's what we're going to use our K-Nearest Neighbor to do over here, okay? To predict whether a cell is actually benign or malignant. All right, so basically that's what we have. That's what based on these features, based on all these features, right? It's going to help us to predict whether a cell is going to be malignant or benign. Okay, so let's proceed from here and then see the various steps that we can take. All right, so if we take the diagnosis column, as I said, it contains some B's and some M, right? Where we have our B to be benign, right? We have our B to be benign, and then we have our M, right? We have our M to be malignant. Okay, so that's what we have. In the diagnosis column. All right, that's what we have over there. Now, if we check the shape of our data, right, you can see that we have 569 records with 32 columns, right? So we have 32 columns. That is 1, 2 from the ID, right? 1, 2, 3. So all the records have been given an ID, right? As they were taking these records, they gave each of the records an ID. So if we take, maybe the first column, for instance, right? So if we want to take this one, for instance, right? So all these records that they were able to record, right? All these records, right? All these records were given an ID, right? They were given all the way to the 32 record, right? So they were all given an ID. You can see for all of them, they were given ID. That's why you can see ID here. Then our target here with all the other features that we have in here, right? So all the way to the last one, okay? All the way to the last. So we have 32 different features in here, right? Remember that it will break somewhere here, so we cannot see all the 32 features, okay? So that's what we have, and then we have we have 569, right? 569. So we are seeing only the first 5 rows, right? The first 5 records, right? So the last one will be 569, right? Or in this case, it's going to be 68 because it's starting from 0 indexing, okay? So that's basically what is happening. All right. Now, if we check the data types that we have here, right? If we check the data type that we have here, you can see that we have almost all of them to be float, right? Almost all of them to be float, with the exception of the diagnosis, which has been indicated as an object, right? And then the ID, of course, the ID should be an integer, right? But all of them are decimal numbers, so they've been indicated as floats, right? So if we go up and then see what we have over here, right? You can see that all of them are floats, right? Float data types, right? That's form of decimal points, right? They are all in the form of a decimal point, as you can see, right? It's only the ID that is given as an integer form, right? As you can see over here, and then the diagnosis have been indicated as an object, right? But in this case, we want it to be categorical. It's actually categorical. It's either benign or malignant, right? It's categorical. So we want to we would like to change it from object to categorical, right? So you need to actually process your data to make it, bring it to order so that you can build an algorithm on. Okay. So this is not in order. We need to bring it back to order, right? Changing it from the data type of object to categorical, right? So that's what we will do over here. As you can see, let me show you the output again so that you can actually see alongside. Okay, so if you can actually see over here now, we don't want to create any new column, so we name it the same way so that we will not be creating another column name, right? So in diagnosis, we are using the as type function to change the data type over there to categorical, right? Category or categorical, if you want to call it that way. Okay, so instead of objects that we used to have earlier on, right, now you can see that we're having category. Okay, so we're changing it from object to category because we have categorical data points in there, right? It's either benign or malignant. Okay, it's categorical. So that's what we are doing over here. Now, after that is done, right? After that is done, we can actually check or count how many B's we have and how many M's we have, right? That's how many benigns and how many malignants we have over there. Now you can see that we have 357, right, benigns as against 212 malignants. Okay, we have 357, right? So this for benign, right, and this one for malignant. So you can see that there are more benigns as against malignants, right? There are more benigns as against malignants. So most people I mean, most cells, right? Most cells are not cancerous as against, I mean, some of them which are cancerous, right? So the cells which are not cancerous are more than the cells which are cancerous. Okay. So the malignant ones are the ones that are cancerous. The benign ones are the ones that are not cancerous. Okay. So that's basically what you can actually infer from it. And I mean the data is quite balanced, right? It's quite balanced. So we don't need to think about the data imbalance over here, right? We don't need to worry about that one over here. Okay. Moving on, we will see some of the data sets that will be imbalanced, and we need to talk about it. Okay. But in this case, it's balanced. It's balanced. So I mean, it's the data point. The distribution here is quite reasonable. All right. So we don't need to worry about that. All right, now we don't need the ID, right? We don't need the ID in our data set as we proceed to build an algorithm. We will not need the ID because this is just an ID to, I mean, show these record to be unique, right? To give them a unique ID so that they will not, I mean, be confused with each other, right? So, I mean, building an algorithm, we don't actually need this ID. This ID, you can think of this ID as the same index that, I mean, pandas will give over here, right? So we don't actually need that. Okay, moving on to build the algorithm, we don't actually need that. So what we're going to do is to drop that ID, right? So that's what we are doing over here, right? We are saying that, let me show you the output so that you can actually see it alongside. So we are saying that in df, right, if we go to df, we're using the drop function to drop, I mean, which label we are dropping the ID, right? And then we are indicating that whatever we are dropping is present in the column, right? In the column. So if we use access equals 1, we are indicating that whatever we are dropping is actually located in the column, right? As against if you use access equals 0, showing that whatever you want to drop is in the row, or in the index. But in this case, we want to drop the ID, and the ID is present in the column. So we indicate that access equals 1. All right. So if you see it again, you can see that we don't have the ID again, right? We don't have the ID again. So we drop it and then we store it back to df, right? And alternatively, we could have just indicated over here that in place equals true, and then that should have worked for us as well. Okay, now after that is done, right? After that is done, we want to now separate our data, right, into the target and then the other variables that are going to help us to predict the target. That is the dependent and then the independent in this case. Okay, so now what we're doing is that we want to separate this, right? So let me do it this way, right? What we are doing is that we want to separate this column, right? We want to separate this column, which is the diagnosis column, right, from the others, right? So this one becomes our y. Okay, that is what we are doing over here, right? It becomes our y. Now we could have selected each of these one by one, but remember we have 32, right? We have 32 columns, right? So even if we take this one out, we still have 31. So to select these columns one by one is going to be a hectic work, right? So but if we drop just this one, the rest of them are the same. I mean, the rest of them are the columns that we want, right? So all of the rest, right, is going to be represented as x, right? After we drop this one from that. So that's why you can see that we are dropping that, and the rest will be stored in a variable called x. Okay, so basically that's what we're going to do, because why we are doing this is because we want to actually scale our data, right? So we are going to talk about that in a moment. Okay, so let's just move a little bit down here. Now you can see that we are actually we want to actually standardize our data, right? We're using Z-score in this case, or we want to actually standardize the data. Okay, and that's why we are separating it, because we have our target to be this category. We don't need any scaling or any standardization on that, right? We don't need any standardization on that. What we want to do is to standardize the rest of the data. Now, why we are doing that is that if you look at the data carefully, right? If you look at the data carefully, let me just do it this way. Yeah. Now, if you look at this data carefully, right, we see that we have 12.32, we have 10.660, we have 11.04, we have 11.24, I mean 28, right? And if you see this one, right, just almost in the same distribution with this one, right? And this one a little bit higher. This one too is a little bit. But if you consider this one, see, we have 464.1, 373.2. This is quite huge values. This is quite huge value. If you consider this one, right, you can see that it's very, 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 very small values, right? Very, very, very minimal values, right? If you consider the others over here. So you can see that they are not all on the same scale, right? They are not, all of them are not on the same scale, right? Not on same scale, right? Some of them are huge values, some of them are small values, right? So we cannot actually build the algorithm on this one. It's actually going to have difficulties in here. Now, what is going to happen is that if you remember that we talked about if you take, for instance, the Euclidean distance, right? If we take the Euclidean distance for example, right? What is going to happen is that it's going to measure the distance between this point and that point, right? Between this point and that point, between this point, between this point and that point, right? Between the same point and this point. It's going to do it for all of them, right? Till the last one, okay? In the same way, it's going to do the same thing for this point and that point, this point and that point, and this point and that. Don't forget, we are going to also square it, right? When we find the distance, for instance, we find the distance between 12.32, I'm writing this one, 12.32 minus say 10.60, right? So I'm doing this one, and then we find the square of that plus the same way 12, maybe we pick 12, and then the next one again, maybe 12.32 minus again 11.04, right? Then we find the square of that. We do it for all of them, right? And then we find the root of that. Now, if you're going to do the same thing for this, right? If you're going to do the same thing for this, it's going to be 464, right? 0.1. I'm writing this one, right? 464.1 minus say 3, right? Minus say 3, 346.4, right? Something like that. And then we square it plus the rest, right? Plus all of them. So you're going to do it the same way. Now, what is going to happen is that this one is going to have a huge distance over here, right? And the square of this is going to be huge. It's going to be very huge, right? So we're going to have a big distance here, and the square of this is going to be bigger, right? As compared to this one. Now, what is going to happen if you take the distance between here, right? For instance, 0.06981 minus the next one, which is 0.11470. Now we find the square of that, right? If we do it for that one too, what is going to happen is that this one is going to have very small distance, even if you square it, right? And even this one. But if you consider this one is going to be very huge. So what is going to happen is that this one is going to outshadow these ones, right? It's going to outshadow this one. So the distance between this one and that one will not matter, right? That's what our algorithm will actually do. It's going to ignore the distance between this one and this one, but the information that this one is going to give us, if we do the distance measure, right, is very critical to us. We need it, okay? But however, if we use the distance measure, it's actually going to ignore this one, right? Because the distance between them will be very, very small, which will not make any impact, okay, as compared to the distance between this one. So what we want to do is that to bring all of them to the same scale. Okay, we want to bring all of them to this same scale. In this case, we want to standardize it so that all of them will be having the same standard deviation, right? They will be having same standard deviation. So let's just move a little bit down there and then see how we did this one. So in this case, right, we are going to use what is called the z-score, right? Let me open this output so that we can actually see. Yeah. So in this case, we are going to use what is called the z-score. So in SciPy, right? In SciPy, the stats in SciPy, right? So in stats, we can actually import this z-score. Okay. Now we're going to apply this z-score on the x, right? Remember, the x contains everything with the exception of the diagnosis, right? So we're going to apply the z-score on that. We're going to apply the z-score on that x, right? On that x. Now, if we do that, right, we store it in a variable called scaled, because now we have scaled it. Okay, we have scaled it. So if we apply the z-score on x, we store it in a variable called scaled. Now, if we do scale.describe, now see what we have over here, right? If we look at it carefully, right, let's consider this. Consider the standard deviation over here. You see the standard deviation for all of them, right? If you see the standard deviation for all of them, right, for all of them, right, all the way to the last one, right, you can see that we have a common standard deviation, right? We have a common standard deviation, right? And that's what we want to do, to bring them to the same scale, to bring all of them to the same scale. Now you see that we have a common standard deviation for all of them. That is 1.00 0, right? 880, and then e to the power. And then we have e plus 00. Okay. E plus 0. So you can see that all of them have the same values, right? All of them have the same standard deviation. That's what we actually want to do, so that no data point will outweigh the other, and the information that each column is providing, we will actually get all the information over there. Okay, so it's a good practice to actually do that. All right, and when you want to scale, right, the very first thing that you need to do, right, the very first thing that you need to do is to make sure that you separate your data. So maybe in this case we have it to be B and then M, right? In some other cases you might be having it to be, say, 0 and 1, right? In that case you might be thinking that, oh, they're all integers, so I can just leave it. No, what will happen is that if you don't separate it first like this, right, you're going to run into something called the data leak, right? You're going to run into something called data leak, right? You're going to run into something called the data leak. Now, what is this data leak? If you're going to apply this z-score, right? Z-score is nothing but subtracting the standard deviation. Subtracting the mean, right? Subtracting the mean from each of the original variables, right? Divided by the standard deviation. Okay, so what the z-score is actually going to do is that it's going to consider each of the data points, right? Let me actually bring it up. Okay, let me do it a little bit like this, and then bring it back. Okay, so what the z-score is actually doing, right? Let me delete this one because I need space over here. Okay, so what z-score is actually going to do, as I said, z-score is nothing but if you pick the z-score, is nothing but subtracting the mean from each of the original data points, right? From each of the original data points, and then you divide it by the standard deviation. Okay, so what is actually going to happen is that if this one, let's say this one was supposed to be, say, 0s and 1s, right? So 0s and 1s. In this case, it's actually in the form of a character, so we can easily see that we don't need to do that. But in some other cases, might not be B and M. It could be 0 and 1, right? It could be like that. I mean, later on, we will even change this B and M to 0 and 1, right? We will change that. But in this case, if maybe originally we were having it to be like that, right? Maybe something like that, okay? You might be tempted to scale everything at once, right? That's where you are going to run into what is called the data leak, right? That's when you're going to run into what is called the data leak. Now, what I mean by that is that if you apply the z-score on all the data points before going to do the train test split, right? Before going to do the train test split, what is happening is that even if you split your data into, say, 80%, right, for training and then 20% for testing, right? What we want is that we don't want the algorithm or the model. We don't want the model to actually know anything about this before we use it for testing, because this is what we're going to use to test to see that our model really learned from this 80%. So we don't want our model to know anything about it. But if you actually divide your data, if you scale your data first, right, before dividing it into 80, 70, right, using the train test split to split it into training and testing data, right, what happens is that during the scaling, the testing column, which is the target, right, if you consider everything without first dividing it in this case, right, without first doing this, right, what is going to happen is that the z-score is going to use that, right? You're going to use that in calculating. Remember that when we finish with this code, with this z-score, they were all having the same standard deviation. I hope you remember that, okay? It's going to consider each of the points in calculating this, right? In calculating this, it's going to consider each of these attributes in here, right? In doing that, right? And that's why we came into a conclusion of having common standard deviation for all of them, okay? So if we do that, right, if we apply the z-score straight away to all of them, to all of your data points, without first splitting it in this way, right, your model will, however, still get a taste of your target. It will still get a taste of your target even before you use it for testing. So it's going to perform very well on this testing data because somehow it has seen it in some way. Because when you're scaling it, right, you first allowed the data to be scaled, on all of the points, right? So your model will still, as it is learning from this, it will still have a taste of this one inside this one, okay? Because you have scaled everything together before coming to separate them, right? So whatever scaling that happened, right, it happened on all of these, right, right? Then later you just separated it. So somehow, even though you have separated it into 80, 20, don't forget that during the scaling they were all together, Okay, so your model after your model is learning from this, somehow it is getting a taste from this one. Okay, so you're going to end up having what is called a data leak. Okay, and in order to prevent that, you can first separate your data into this format, which is maybe training, right? And then maybe independent and then dependent, right? Or maybe it's just the target, right? And the other attributes. Okay, so that's actually a good practice to do in order to avoid this one. All right, so I hope you have a little bit intuition of that, right? As we progress, we'll be discussing more of that, right? We'll be discussing more of that. If we get to the project part, you'll get to understand what I mean by this one the more. Okay, but I hope by now you have an idea, you have an intuition about that. Now, what I'm going to do here is that I'm going to actually convert everything into a data frame, right? I'm going to convert my scaled data over here after I scale it, right? I'm going to convert everything back to a data frame. So if I do that, and I see the head of it, right? You see that now I have everything in order, right? You can see that no other data points, even with the area mean, which was having huge values, right? If you see the area mean, right, or area mean over here, you see that's it's not that huge numbers as it used to be over here, right? As it used to be over here, so it's not going to outweigh any of the other columns. Okay, they are all in the same scale, right? Now they are all in the same scale as you can see over here. All right, so we can progress and then build algorithm on this one.